introduce my 2007 BMW 335i. This car was built as a budget 9-second drag and drive car, and it was completed about 4 months ago. In its first month, it set the world record as the world's fastest twin-turbo N54 with a 9.5 second pass. And in the following 3 months after that, so a total of 4 months it's been on the road, it's racked up about 10,000 kilometres or 6,000 miles of highway driving between racetracks, mostly towing its own support trailer all of that time and through the middle of a hot Australian summer. It's done around 50 full power passes down the quarter-mile drag strip, as well as 50-odd full power passes at different roll racing events, and I haven't seen any issues. The engine temperatures have been fine for all of the driving on the road and the track. The only time I saw a problem was about a month ago when, in very busy traffic towing a trailer on a hot day, the alternator regulator failed, and that caused the water pump to stop and the fan to stop. By the time I realised and pulled over, the coolant temperature was already at 130 degrees Celsius or 266 degrees Fahrenheit. But it didn't blow the head gasket, and I've since had it back on the track and haven't seen any issues that have come from that. But generally speaking, it doesn't run any hotter than I would have seen before doing the epoxy. So I'm going to start this video at the end of the process. I've already finished closing the deck on this N54, and I'm going to talk about why we've done what we've done and why it's important to do it this way. Now, if you're not interested in all of that science stuff, then you can fast forward this video and just go straight to the hints and tips, and you can follow that to end up with the result that I have here. So let's start with what is an open deck. This is the deck, the top face here, and it's open because this gallery down this side of the bores is normally not full of epoxy. It's an open gallery down this side and an open gallery, coolant gallery down this side. So that makes it an open deck design. It's open deck because for two reasons. One, cost. It's cheaper to produce an open deck block. To cast an open deck block with this open means that the casting process is simpler and more cost effective. That's really all it comes down to. There is some downside to it, but BMW overcome that downside or those controls by using the head gasket, by the design of the head gasket. So I'm going to come to that later, but it's easier just to cast it all open and then deal with the problem later using the head gasket. More recent engines like the B58 are closed deck, but BMW has had to spend a lot of money and engineering time to get the closed deck exactly right for the right thermal efficiency. And in the N54, it was easier just to cast it all open and then deal with the thermal efficiency by using the head gasket or changing the head gasket design. So that's the first reason. And the second reason that it's open deck is simply because they can. This was able to hold the power that they designed for the engine, so no need to make it closed deck. That's the reasons why it's open. The reasons now that we're going to close it, or why we want to close it, and it really comes down to power and providing structural rigidity to the top of the cylinder bore. So why does it distort? There's really a couple of reasons for it cracking or distorting, and the first one is just simply it's the pressure in the top of the cylinder. We are going to produce more horsepower. More horsepower requires more pressure. And so there's going to be extra forces acting on the cylinder walls around the top here, and so the reinforcing helps to prevent any distortion or cracking just due to that extra pressure. Secondly, it helps protect against knock or pinging or pinking events. So there's two types of detonation: pre-ignition, and the second type is known by three names: knock, pinging, or pinking. And knock, pinging, or pinking happens when the spark plug fires, pistons near top dead center, the spark plug fires, and you get a separate uncontrolled detonation event, normally around the sides of the chamber, and that is effectively an uncontrolled explosion with a lot of force, and it can exert that force on the side of the bore. So once again, this is now an extreme amount of pressure around the edges, the top edges of the bore. Now it's probably an appropriate time to sidetrack and just talk about the knock sensors, which are located on the intake side of the N54 block. And there is a theory that with closing the deck, these sensors will become more sensitive to knock events because there's a solid material at the top of the cylinder, or between the top of the cylinder and the block wall, to transfer those knock signals. But I can confirm that in my case, I haven't had to desensitize the knock tables, and that's probably because I've got a good tune that isn't creating knock events in the first place. So just to now reiterate how deep this channel or groove or canyon is down here, this little training guide here we go. So the black area of the cable tie is the open area, and the little yellow and green electrical tape is the closed section, and obviously the white's what I'm hanging on to. So that's the depth of the gallery, and we're just closing the top section where that yellow and green tape is. So regardless of what hole we stick that down, that's where it sits. And you can see here the thickness of the deck, the closing of that top deck. So in my case, it's about 17 millimeters thick. I was basically trying to cast it to be 19 mil, but it sits just, you can see, a millimeter or two below the surface there. And so the end result is I've got, I don't know, 16 or 17 millimeters, maybe 18 millimeters of material thickness there. So that's just supporting the top section of the bore. So that's the second reason, is that knock, pinging or pinking events, to help protect against that. The third reason is cylinder distortion that happens, sometimes called ovaling or rocking. So the piston here has a rod attached to it, and when it fires, it's slightly off center. So that can sit like that in the bore, but the rod is actually not directly sitting below the piston. It's got to be off to one side slightly as it fires. And what that means is that you end up exerting pressure or extra forces on the sides of the bores here. As that piston's, as the explosion happens and the piston is pushed down, it's actually pushing a bit of extra force onto the sides of the bore and trying to oval the bore, widen it out here. And so the epoxy helps to obviously prevent that from happening. And even BMW have, I think, in their design, I'm just trying to reverse engineer what they've done here, but these cylinder walls are not concentric with the bore. So let's move around this way just so you can understand. So BMW actually designed it. Sure, it wasn't just a mistake in their design, but this is 10 millimeter thickness here. So first of all, there's two parts. There's a steel liner and the aluminium cast on the outside. So as I understand, they are casting the aluminium block with the steel liners in place. So there is a steel liner here. That's another thing. Some people believe that the N54 is a treated bore, an aluminium treated bore. It's not. It is a steel. There is a steel liner here, which does mean that honing, and that makes the process of honing simpler and much cheaper, that you don't have to reapply that special coating that is on some other BMW engines. But you can see aluminium here and a steel, just the different colors. So it's 10 millimeter thickness up here. So remember, those forces that are trying to oval the bore are this way and this way. They're not really on the ends. And so it's 10 millimeters thickness total there, 8 millimeters there, 8 millimeters there, even 7 here. Now, admittedly, there is two steel liners close together, and steel is stronger than aluminium. It's 11 at the front here, around there, and so it is. There is a thick section here. At the back, it's even more. It's probably 12 or 14 millimeters. But yeah, it is, as we then look across the bores, excluding the end pieces, it's the same gets replicated over and over again. 10 millimeters on this edge, 10 millimeters here, necking down to 8 millimeters, and then 7 in the middle. And so there is already extra material there, I think, to help support the engine with those forces. And so that's really our three forces or things that are going on with the engine, and what we're trying to stop. I will also say, actually, I need to point out that there is a potential rocking force of the cylinders. So the cylinders are not supported all along. They're joined together. You see that? The line of them, though, they stand like dominoes here, all attached together. But the line of them, they can rock side to side, especially through the middle here. N1s less so, because they're attached with webbing to the outside of the block. But through the middle here, these middle cylinders can actually, through those forces that are pushing sideways on the bore in that direction or that direction, can actually push this over. And by pushing that over, I think it's going to create integrity issues for the head gasket. If the cylinder head is not moving, but the bore is moving, the head gasket's pushed down on that, you're going to have a potential blown head gasket from the rocking forces especially of these internal cylinders. So hopefully that highlights why we're doing it, and why it's related to higher horsepower. So if you're 300 horsepower, 400 horsepower, it's really not needed, because this material is able to withstand that, the existing material. So it's only when we go up to those higher horsepower. There's no magic number. Everybody wants to know, what horsepower do you have to close your deck? I used to believe it was about 800 horsepower, but now I'm coming to believe, through advice of tuners and so forth, that actually 700 horsepower and above is probably where you want to really start considering it. Of course, you'll hear there's people out there running 1,000 horsepower on an open deck or whatever. The question is how long they can do it for. And there's things like those knock or pinging events, depending on your tuner and other things going on in the quality of your fuel and ignition system, etc. That could be, that sort of an unknown that could affect some people more than it affects others. So we've decided to close the deck and fix those potential problems I just described. However, there's no point fixing them if we create another issue, especially if that other issue is related to the cooling system operation. Now, we need to keep in mind that the number one reason for blown head gaskets on all engines is overheating. So I'm not saying it causes all blown head gaskets, but that's the number one reason, is overheating. And so it's, for me, this engine is being built for a car that I'm going to drag and drive. So I'm going to drive 500 miles to a racetrack, put my 700 horsepower down the quarter mile, and then drive it home. I'm going to be towing a trailer, driving it in summer up and down hills, and if it overheats on the way to the track, then what was the point in doing this in the first place? Now, keep in mind as well that some people have done this and saying they don't have overheating issues, etc. And their only real judgment of that is that they haven't maybe blown the head gasket, at least not yet, or that they're referring maybe to their engine oil temperature on an N54, or even their coolant temperature. Maybe they're monitoring their coolant temperature, and their coolant temperature doesn't show that it's any hotter than it was before they did this job. Now, that's, in my opinion, not conclusive at all, because there is only one temperature sensor in the engine, and it's not even located in this area that we're messing with. So your sensor might read the temperature is fine, but you might actually have small overheating issues in one part of the engine and not another. And hear me out, we're going to go over it. And the end result is I'm going to show you, or hopefully convince you, that why I've done the holes the way I have, the size and position of the holes. And so let's understand the cooling system operation. Now, I'll try and explain to you how I understand the N54 cooling system works, using perhaps some of my knowledge as a mechanic, some of the studies I did in physics and thermodynamics at uni, and even more recently in irrigation automation design. So we'll start with the pump here. We've got the water pump, and it has an impeller in there. Try and get the camera to focus. You can see an impeller down there. So the coolant comes in here, that's spinning, pushes coolant out through this outlet. Now, it is an impeller style pump, so it's not a positive displacement pump. What that means is that the impeller can spin and we can get no flow, we can deadhead it, and we won't stall the pump. So of course it will burn more energy, and it's going to really put a lot more pressure on bearings, etc. The point is that it's not positive displacement. You can actually restrict the flow of the pump and it will keep operating, just at a slightly higher pressure. So coolant's going in there from the radiator. The coolant comes in there from the radiator and comes out here. After it comes out here, we end up in this line here, in this end of it here, this rubber hose here. So the coolant's flowing through this line here, and I can't hold it exactly how it's supposed to sit because my cylinder head's in the way, but that then flows into the side of the block. So we're going to come back and look at this later, but this particular piece. But now coolant has entered the block there. So I've got a torch here. Let's try and highlight what's going on. You can get an idea now of what there's a V-shaped wedge here at the entrance, which sort of splits the flow to the left port or the right port. It ultimately goes into a common cavity. The left and right are connected up the top here. If the epoxy wasn't in there, you'd be able to see that they are actually connected. So it is a common cavity that it's going into, but it is directing some to the left and some to the right. So it's now, the coolant is in this gallery here, or call it like a little canyon. It's in there. Now it needs to get from there through the engine and ultimately out a port over here. That's the exit port for the coolant. So it can't travel through between the cylinders. There's no holes. I can't show you, but there's no holes in that gallery to this gallery between the cylinders. There's no cavities or openings underneath. It can't flow down and under and back up into this side. The only way it can get over that side is actually by flowing through the cylinder head, and that's where the coolant is doing most of its work, is actually pulling heat out of the cylinder head. So we've got the cylinder head sitting there. It's basically just taken off the engine and flip over that way. So the ports on this side of the cylinder head align with this gallery. The ports on that side, the outside of the cylinder head, align with this gallery. So so far we've got to coolant being in this gallery here, and from this gallery it's going in through these ports here. So this opening in the cylinder head sits above, for example, that hole there. So coolant is going to flow through that opening there into the cylinder head, around there and out through these holes. Now it is one common gallery in there. It's like a big ant's nest in there, in that water can go in that port and out this one, or in that one and out this one. But ultimately what BMW is trying to do is get the flow from one of these in one of these ports, and that flow to come out on through these ports. So it's flowed through the cylinder head. It's picked up a bunch of heat in the process, remembering that this is on top of the combustion chamber where all the heat is being produced, and so there's a lot of the heat removal is actually happening in the cylinder head. The coolant comes out of these ports here. Now it's hotter than what it was before. It's dropped down into here. We've drilled some holes to get it down into that gallery. But if the closed deck wasn't there, it's just dumping it into this gallery down this side of the block, and then it flows and moves to the end here, and it comes out through, well, what I've now made a hole here. Of course, if it was open deck, that's all open, but that hole there then aligns with this hole here, which flows in there, around and out this line, out this side, and that then goes to the top of the radiator, where then it flows through the radiator, it's cooled, and comes back into the water pump, and the process starts again. So pretty straightforward. However, although it looks like all of this, that BMW, you know, here they've split the flow what looks evenly left and right, 50-50, and we look here at the cylinder head, these openings all look pretty much the same size. There is some slight difference. This one actually, when you look carefully inside of it, it's a bit smaller than this one at this end, but generally they're the same size. This one's got a little bit missing here. This one's got a little bit longer there. But apart from that, you'd say it's even flow. They're pushing the flow in 50-50 each way, and then it just flows, you know, certain percentage, same percentage through each of these holes, out those holes, and out this side. Now, it's not true, and although that was the easiest way to cast it and make everything, what BMW has done is actually using the head gasket to control the coolant flow. So let's grab the head gasket, and actually we'll start by putting it on the cylinder head. So carefully set that down there. Get it all lined up. Okay, that'll do. It's not exact, but it's close enough. So remember those 6 ports are all the same size in the cylinder head? Have a look at the head gasket. Have a look at the size of that one versus the size of that one. And the fact that there's an extra one here that wasn't, well, there's only a small hole down on this end, but there's a extra large hole, you know, there's an extra, this hole at the end is actually a lot, is larger. So they're actually using the head gasket to control the flow through the engine. So if you follow most of the instructions for these epoxy products, which just have consistent, the same number of holes drilled all the way around, then you actually end up in a state that potentially you could end up with overheating issues in part of the engine, and I suspect it's going to be at the back of the engine. So this is cylinder number 1, the front of the engine. Here's the back of the engine. Your gearbox is going to be there, and why I say that is that the coolant's going in here, but the low pressure point is over there. That's where effectively the coolant's getting sucked out of the engine. So the shortest path to go is through here, across here, up over these cylinders, dump down into that gallery and out the port. And so the system will naturally favour, if the head gasket holes matched the openings in the head, then the coolant will naturally flow or favour the shortest possible route through those 3 cylinders and then out the exit port. And that would mean that these cylinders are going to overheat, and not just that, but the flow through here is going to pick up all that heat, and it's got to carry it all the way down that end there. So you could end up with hot spots and cold spots in your engine. And so just for the cooling system alone, we're going to come to another reason to do with this line here, turbo line. But what BMW is doing is they're creating here larger holes for more coolant to flow through this cylinder. It's got further to travel, but it's a path. Let's say it's a path of least resistance by having bigger holes there. It's more of the flow is going to go that way. So you're going to end up with a higher percentage of flow going through here to cool these than you will up the front there, because it's got a further distance to flow. Hope that all sort of makes sense. Larger holes here, also larger holes there that I've made that replicate or I've tried to use a ratio sort of method. I can't make my hole here exactly the same as that size hole, but the ratio of that hole and that hole is matching sort of the ratio of this hole, a small hole, and a small hole here. So yeah, hopefully that makes sense, the understanding of how BMW is controlling the flow of coolant. And that's why it's important to try and mimic that, at least in the ratio of the size of your holes, on both this side and that side. But especially on this side, when we look at it, that's these ones here. They go from small, a little bit bigger, to potentially a little bit smaller, a little bit bigger, quite a bit bigger, and then extra large, and then this extra large or larger hole at this end. And so that's what's replicated along this side here. On this, and I'll wait till the end of the video, you're going to get a slow-mo video of all these holes to know where to put them. So finish watching the video and you'll get some close-ups. The other thing I've done is because we've got this meniscus, and the fact that the the epoxy is not level with the top of the aluminium, we've got potentially little pockets where coolant could sit and overheat, where it's not actually flowing, it's not moving, and we've got a point here. So although there's no hole in the head gasket at that point, so that's this point where my finger is pointing, there's no hole in the head gasket there. I have put a tiny little 2mm hole in the epoxy to ensure that if there is a little pocket of coolant there that's getting hot, there's a chance for it to escape using that hole. And the same here. There's 3 little holes here. So on the head gasket, we've got holes in the these little indented areas on all around the cylinder head, all the points, except for here, here, and here. So those 3 points are, flipping the head over, that's what aligns with these 3 points here. So I've put these little 2mm holes here because I don't want a little pocket. Remembering the cylinder head's there, it's going to be very shallow. It's going to be a little 2mm deep puddle, and if the coolant is flowing, it will flow around it, but it might create a little hot spot there right next to the cylinder. So these little 2mm holes are just to help evacuate any extra heat or pressure that might build up in those little pockets. And on this side, with these holes, so let's start looking at the head gasket. We've got, well, let's first of all, we'll give these slots some names. So this slot, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All of the slots in the middle, except the end ones, are the same size. So that's the same size as that, etc. Just that the one up this end is smaller by about 30% or 50%, and the one at this end is bigger by about 30 to 50%. Once again, aligning with the need to move more coolant through at this end of the block and head versus that end. And so here, for all the middle, all those middle slots that are all the same size, I've started by drilling 3 holes, putting my head gasket over. So all of your holes should align with your head gasket. Now, so larger hole here, just recap that, larger hole. You can see that my holes underneath is to a similar sort of ratio, favouring coolant coming out here like the head gasket does, similarly next to that hole there. These holes here have similar, move that aside, they all get holes like this drilled in them, the same with those ones on that side. It's just those extra little 2mm holes along those top 3 sides. So let's put that back in place. So these slots here, I started by drilling 3 holes, marking and drilling 3 holes. One on the extreme that side, one on the extreme that side, and one in between. One on the extreme, basically just marked it with a marker, and then just by eye drilled 3 holes. These are 4mm holes, 3 4mm holes. And then I've joined 2 of the holes together, this hole and that hole, leaving the bridge intact here, just to once again help with that structural rigidity that we're trying to achieve. But this is opening it up probably significantly more than what it would be just by drilling 3 small 4mm holes. And so that's the same all the way along. At the very end here with this smaller slot, it just has the 2 small holes, and that's right next to the exit anyway, so coolant is naturally, it's going to have a low pressure point there, it's going to get almost pulled through those holes. At this end here with the larger slot, these are I think 5.5mm holes, 3 of them, and then I've joined those 2 together. I did drill that one slightly closer to there, and making a large try to make a larger slot there than what I've done there, to once again favour the coolant flow over the back of the cylinder head, the back of the engine there. Now, the other thing about the pump and just drilling these holes, or only putting a small number of holes in there, is that you're creating a restriction for the pump, and I'm effectively doing that because I haven't completely opened these up to match the head gasket. It could be an idea to, if you wanted to, you could join all those 3 holes together and have a larger slot there. I'm sort of going to err on the side of caution and go with this option. But if you only drilled 3 4mm holes there, for example, you're trying to push all the flow of the pump through all of those tiny little holes, and it's going to put a lot more strain on the pump. The pump will then, the flow will slow down, so you're going to get less coolant movement through, but also the pump is going to work a lot harder, and you are going to wear the pump out sooner, and it's going to fire up more often. So for the sake of longevity of $1,000 cooling pump, extra holes are really, or larger slots here, are really going to help. Now, you could argue that it's going to affect the structural rigidity, but remember where those forces were acting. Even they're more on this end here, so we've still got a good sized bridge there, and here we've got a lot of support around the sides of it. So the hole is right in the center line there, in the middle there, but there's a lot of support around it. So I'm confident that we're finding, I guess, the balance between rigidity and supporting the block, the tops of the cylinders, and the coolant flow through it. The other thing is that I haven't machined anywhere the epoxy right back to the aluminium. So I've tried to always leave a few millimeters. Some cases it's probably only down to 1.5 millimeters or 2 millimeters, but I definitely don't want to completely break the epoxy between the points. So I think that's important for its rigidity and its structural integrity. And it will be a sign later that if I see cracks in it, if I ever have to pull the head off and I see cracks in the epoxy, then I'll know that, there was significant forces acting on it. Whereas if I've ground out these slots all the way up to the aluminium, then I'm maybe not going to have an idea. So that's just my thoughts on that. So that was a summary of the coolant system as it relates to the block and the cylinder head. But there's another part of it, a little diversion, and that is for the turbos. So from this line here that brings the coolant from the pump in through here and out there into the block, you'll note that there's 2 ports on the underside of that. So if I turn that up, there's a Mickey Mouse fitting somewhere else, and I think this one's the Freddo Frog fitting, but those 2 ones that would be the eyes of Freddo Frog are feeding coolant. I don't want to damage my head there. They're feeding coolant into the turbos. So it's coming in the main pipe here. There's 2 little holes in the bottom of that. So the coolant comes in, it reverses flow, comes back out and around on a coolant feed line that feeds cold coolant or cool coolant to the turbo. Goes through the turbo, removing the heat from the turbo, and out this line here, just the rear turbo, and into the block there. So that's just below that point at the back of cylinder 6. And the front pulls coolant around through the coolant feed line to the turbo, taking the heat out of the turbo. The hot coolant comes out on this line and into the block there at cylinder 1. Now, cylinder 1 is less of an issue. You still need the hole, of course, in the epoxy there to help carry the fluid over, but this is the shortest route to the exit point, so there is always going to be some favoritism towards the flow here, and we shouldn't have any problem keeping coolant flowing through the front turbo. But for the rear turbo, if you made this hole back here the same as the front, then you're going to restrict the flow here. And what that means is that it's possible that you won't have the necessary amount of coolant flowing through your rear turbo and cooling it, and you'll overheat your rear turbo. And it's important then that so this hole is larger to ensure a lot of flow is going over, which creates a larger hole there, creates a low pressure point here that actually pulls the coolant through from the turbo through here, effectively sucks it through like a venturi and through into the head, and off it goes. But also that there's not hot coolant here, so a larger amount of flow coming through here means that the coolant flowing through this part is going to be a bit cooler than the coolant that is in other parts, just because of the higher rate of flow. And thermodynamics tells us that hot flows to cold. So if there's hot coolant in this line here and there's hot coolant in there, we're possibly not really going to have flow. So to help try and pull the flow through, we need large hole there so that we've got a cold point or a cooler point there, and that way the hot coolant in the turbo actually gets pulled into that point. So that's just my summary also of the importance of these holes as it relates to cooling the turbos, particularly the rear turbo. For those that are wondering about this pipe here, I need to point out this is the version of this pipe for a manual car. Now my car is auto, it's staying auto, but I'm going to change to a manual radiator and put an external transmission cooler on the car. So I'm going to use this manual pipe. The auto pipe has can't remember where it comes off, underneath or on top, but there's an extra line attached to it. It's actually an exit line that takes cool water to the heat exchanger for the transmission. So if you're looking at this pipe thinking it looks different to yours and you're an auto car, that's why. So it's just the version for the manual car. Now, some people have talked about trying to brace this front section of the block. So cylinder 1 here, front of the block, timing chain in here. Now, we'll just point out this is where potentially there's less strain. It does have a webbing connection to the outside of the block, so it's much better supported than, let's say, this section in here, which doesn't have any connection to the outside of the block except going all the way back to here, or down and underneath the cavity. So this section here, some people are putting a block in there and then a bolt out here and bolt through here to help hold a machined piece against this wall. Now, I do think it might help, but really it's not going to be that effective in my opinion, and it's not really worthwhile. From what I can tell from all the research, trying to find anybody that's blown this part of cylinder 1 out is actually pretty rare. There was one example of Gasson that did it when you hydrolock the engine. I think a problem with an injector or the fueling system, it filled the bore here with fuel and then it compressed and had to go out somewhere, and it did blow this out. But that was quite a unique example. When hydrolocking an engine, if it didn't blow that out, that was something else. It was going to bend a rod and do some other major damage anyway. So I really don't think it's necessary to support that, and if you did and you did it that way, I don't think it's that effective, because this main wall here, apart from the webbing along the top edge, this is actually not very well supported. It's relatively thin through there, and it doesn't have support until you go down to these points at either end. So this is a big wide section, fairly thin material. Putting a bolt through there to support that, it's just gonna flex out here enough that you'd still get a crack in the liner, in the bore there, in my opinion. But the next thing to cover probably is maybe the difference between epoxy and aluminium. Now, I've made a separate video on testing the strength of the epoxy. We can debate that all day long, whether it's as good as aluminium, better or worse, etc. But I do need to point out that there is some differences about how the deck is closed, or effectively of the closing of the deck. So the way the epoxy is normally done is like I've done it. Now, I did do it after the top of my block was machined. Technically, it would always be better to machine your deck the top of the block here after doing the epoxy, just to take any, if there was any that spilled over the sides, just to get it off and make sure there was none protruding. But generally, when you're casting the epoxy, you end up with this meniscus effect. I'll try and move the camera here. So you see the epoxy sort of ramps up to this lip. It's the same as what water does. It's called meniscus. It forms, it's that rolled edge just there. So this is sitting lower than the deck there. So bring it down, camera down on that angle, you can see this surface is lower than that surface. And so the epoxy is not actually here, it's not in contact with these extra surface areas of the cylinder head. So there's a surface area there where the epoxy is not actually touching the cylinder head. But in the case of aluminium inserts, those inserts are placed in here and then machined with the rest of the deck. So they end up exactly the same height. So you basically have a consistent surface all the way across this gap, across this gallery. And what that means is that there is material that's able to hold the head gasket against this point, for example, in the cylinder head. So you get more clamping force on your head gasket. So that's a pro or advantage to using aluminium inserts as opposed to epoxy. However, I think that's a minor reason, and the BMW MLS style head gasket is known to withstand 1,000 horsepower with this type of setup anyway. So it's not really an issue for the head gasket on the N54. But if you're really concerned, then yes, aluminium inserts do offer a slight advantage in that area. I'm going to film here all of the holes. Let me just zoom in. So start there, and you can just pause the video at any point. So where are we up to? Cylinder 3, 4, 5, 6. And now filming it with the head gasket in place, so you can get an idea of where all those holes align in relation to the head gasket. It's not going to be a how-to video. I'll just provide some links in the description from the supplier of this material, and you can watch those. But perhaps I'll just talk about my interpretation of those instructions and some of the things that I found that may be worth noting if you're going to do it. So first of all, obviously I've already got the epoxy in there, so you can't see everything that's going on. But what I did is I took some sockets like this one, wrapped them in tape, and then wedged them into the turbo coolant ports in the side here. So these ports have coolant. These are a coolant port for cooling the turbos, and we need to keep them open. I'm going twin turbo, so I need both of them. There's one here and one, where are we? One there. And I need both of them to be clear and open. If you're going single turbo, then it's a different story. But for twin turbo, you need both those clear and open. You do not want any epoxy getting into that hole, anywhere in that hole, because then your O-ring isn't going to seal, or even your coolant line isn't going to even push into the hole. So just for reference, that's the coolant, the turbo coolant line, and this end here is going to plug in there. So let's take that out. Oops, I'm going to fall on there. And that's going to plug into there like that. So that O-ring needs to seal inside that hole, and there's another one up here, similar sort of hose that plugs in there and needs to seal in that hole. So we don't want any of the epoxy getting into that hole from above when we pour it. So the socket with the tape on it, wedged on it, going in there, wedge that in there, one in the other hole. And actually in this hole as well, this is a coolant port that we've got to keep open, is in the video I think they just put some tape over it. And I think even in their video there's bits of blue epoxy showing up, coming through the sugar or somehow down in there. And so I actually got some rag and shoved it into these holes just to absolutely be certain that nothing would come out. So I cut up some piece of rag and shoved them in there, and then put the tape over the top of the hole. And on the back of the block here, there's this one here, and I put that plug into place in there. So they're all the holes, I guess, you've got to fill. And so with the socket in here, it's actually the end of the socket would if the epoxy wasn't there, is visible. So then I put sugar in and filled the sugar up till it was 19 millimeters from the deck surface, 3/4 of an inch all the way around. And they were the end of that was quite visible in there. So I just carefully just layered and piled up a bit more sugar just to barely cover that. I could sort of just see the aluminium of that showing through the sugar. And that's how I set the level. To verify or control that sugar level, this is what I did. Just had a wooden pencil with a bit of masking tape wrapped around it. It's 19 millimeters from the end to the underside of the tape, and I just hold that there with the sugar in. Obviously it sits down inside that gallery, and just slide it around, running that along the edge, sitting it effectively on the edge of the aluminium. It's almost, well, actually I'll probably show you on here. Just sitting that on the edge like that, and running it along like that to smooth out the sugar and get it all to the right level. Another idea, if you're happy to use a piece of metal, is to get a bolt and a nut, screw it on so there's 19 millimeters of thread showing, and then you can just roll that along and set your sugar to the correct depth. So a couple of tips on how to get a consistent depth from the deck of the sugar. Now on that, I chose 3/4 of an inch for my depth, which, as we know, ended up being 17 odd millimeters of actual material thickness there, just under, I think it's 5/8 of an inch maybe. And I chose that rather than a deeper. There would have been enough epoxy for me to do maybe close to an inch, I reckon, maybe more. But I chose that 3/4 of an inch because I think that's sufficient for supporting the top of the cylinders. And any more than that, and you start to maybe rob some of the cooling capacity of the system. So if it was an aluminium closed deck using aluminium inserts, they're about 1/2 inch thick. So yeah, err on the side of caution with the epoxy. I went 19 mil. Now we've done the tests of the strength of the epoxy. Would I change my mind? Probably not. I think I'd probably still happy with that 19 mil. It probably could go less, maybe 15 mil. Probably wouldn't go much less than that, and I still don't think there's any point in going much more than that. So even if you're single turbo, I think the 3/4 inch depth is probably sufficient, which ends up at, as I said, at about 5/8 or 17 millimeters. Keep in mind that there is that meniscus that forms. So you can see there that the level is down here, but it rides up the edges just naturally. And so when you've got your tape on here that's, I don't know, 1/3 of a millimeter, maybe 1/2 a millimeter thicker, you can't afford to go above this surface. So you're not going to the top of the tape, you're going just underneath the tape when I did this. So just keep that in mind as well. If you end up going higher than the tape, then it probably wouldn't be a big deal if you hadn't had your deck already faced. And in fact, that would have been a better idea for me, would have been to do the epoxy and then get my deck faced, but I got it the other way around. If you did get the deck faced afterwards, then any extra epoxy that's sticking up proud will just get machined off, which isn't a bad thing. So if you are going to get the deck done or get the block decked and this surface cleaned up, then perhaps do your epoxy first as a safety margin. It was very nerve-wracking that you didn't want to end up with any epoxy on this surfaces here, so spent a lot of time with the tape, putting the tape on and cutting around to get a nice finish to work with. Yeah, once the epoxy had set, then yeah, I pulled the sockets out of the holes there. Yeah, I didn't have any any epoxy anywhere inside those holes. Once it's set, of course, peeled that off, pulled the rags out of there, pulled the plug out of the back side, and yeah. Then once it's set, so I followed all their procedures and let it set. I think it was 18 or 24 hours before I even attempted to drill the first hole, and to be honest, I'd probably just suggest waiting 36 or 48 hours. It was about 4 or 5 days later when I finished them. Here it is with a stock BMW MLS style head gasket just sitting on top here. And yeah, you'll see in the video, you put your head gasket on and trace around to know where to drill it. But in this area here, I noticed, well, of course, the hole in the head gasket is quite large, and just a 3/8 hole was in the instructions to be drilled there. And I don't agree with that. I think this hole needs to be a larger. In fact, you know, I'm still even worried maybe I could try and make that a little bit larger again. I'm just worried about yeah, it getting too thin around the edges and breaking away. So I'm reasonably happy with it that size. At least it's better than the 3/8. The main reason is that that's a primary coolant exit port for moving coolant. So the cylinder head goes on here, and this is actually the gallery in which the majority of the coolant, or all of the coolant, flows out of the engine and across to the radiator. For this process, I've found that it's best to put it on a nice sturdy workbench. So in my case, I've got this welding trolley here that weighs a ton, and it's got a big solid top on it, and it brings it up to a good working height, and it's solid. You can push down on it with the drill and it's not springy. I found that when I started this process with the engine on the engine stand, it's a lot lower, you're leaning over a lot more, and it's sort of spring loaded, especially when you're working, if the engine block is bolted on here, when you're working at the opposite end, pushing down with the drill, it's very springy. So best thing, find yourself a nice solid workbench at a good height. So for me, this is, well, just above belly button height, let's say, and it makes it a lot easier to work on. And make sure you've got yourself a good light to illuminate the process. This is just a plastic trim tool. It's about 3 or 4 millimeters thick, so it's plenty thick enough. And basically just use it as a safety measure. Just keep pushing down to drill, and when it breaks through the bottom, there we go, no damage to the block. So even if the drill drops down hard, it just hits the plastic, and everything underneath. Actually, let me move that out of the way. There we go, no damage to the block. So I'm just finding I'm starting with the smaller drills and then drilling them out bigger. That seems to be working best. In the video, some of the instruction videos, it talks about like hot chips of this stuff coming out and burning things. Hasn't been my experience. It's been like almost a very fine powdery substance as it drills through. It does blunten the drill bits very quickly, or can do. I'm finding starting with a small one and working up, yeah, damaging less drill bits. Getting the hole started, one of these is actually about halfway through. Get the hole started with that out of the way, and then just move that over once you got it about halfway through or a third of the way through, just as a safety measure for the last part. Where possible, I've just used a larger drill bit to create a slight chamfer on the edges of the holes, and that just might help the coolant flowing through. Just a moment. Now, even with that hole how it was, much larger than the instructions, still not confident it's big enough. I really don't want any issues, and I know that there's all the epoxy in here really isn't offering any extra support. The support is needed across here. So I've used a 2mm drill bit here to go around my area and even make it larger, and then I found the Dremel with one of these sort of bits on the end. Has been working well just to bite into it. So I'll use the Dremel now to eat away at the rest of that all around there, and just try and make this as large as possible. In hindsight, if you're doing it, just start with larger holes around the outside and then join them all together and remove a big chunk all at once. This small Dremel bit has been magic. It doesn't seem to be blunting, so yeah, it did a magic job of grinding out that hole larger. So much so now this has given me confidence to fix something I've been concerned with the rest of the holes, and that is the size, relative size of them. So at the back here I had 3 small holes just like I've got there, and what I've done is I've drilled a small 2mm hole between these larger 4mm holes, and so I've done that here, and then I've used the Dremel to join those two together. So I'm going to have a small hole and then an oval shaped hole, small hole, oval shape. So we'll work through that. Back here, these were already, I think they were 5.5mm holes. They were a bit bigger, so that was 4. These I did as 5.5, 5.5, 5.5. The ends of them are where the head gasket hole ends, so no point going further to the sides, but I need to make it bigger between. So I've decided between these 2 holes, 2mm holes there, use the Dremel and cut that out, join that together to make a larger cavity. And over this side, I really wanted to make a bigger cavity here, so 2mm drill bit there, or 2mm drill hole there, and now I'll use the Dremel there, same here, just to make that larger. So same here, a bit larger there, just working my way around the holes. Some drilling tips for the epoxy. Start with a small drill bit. This is a 2mm drill bit. It's the smallest that fits in the chuck of my drill, and that goes through it quite easily, and so that's a good starting drill. So the biggest that I found you'd want to use as a starting drill is 4mm, and even then I think it's too much. And the reason is because it overheats the drill bit and it bluntens the drill bit, but more importantly, you are affecting then the composition of the epoxy material. So if you're not sure on what that means, you'll have to go and watch my long 45-minute video on testing epoxy, and where we put it in the oven and set it on fire and subjected it to things that it's not normally going to see in the coolant gallery here, but effectively it changed the composition of the epoxy and made it crumbly, and you don't want that. So you don't want to overheat it while drilling it. So if you're getting smoke coming out while you're drilling or grinding it, if there's smoke pouring off, then stop and resolve that issue, because you're only overheating the epoxy and damaging the integrity of it. And I've been grinding it with this little grinder bit in the Dremel, and it gets warm, but it's not burning. You're just biting off a tiny bit at a time. It's very time consuming. Start with smaller drill bits and work your way up. So if you've got a hole to drill that's, I don't know what that one was, 8mm or 9mm, 8mm, start with a 2, then a 4, then a 6, then an 8, and work your way up, and you'll find that it's a lot easier on your drill bits. Your drill bits will last longer. You'll be drilling more holes in it without new drill bits, but also you won't be overheating the epoxy anywhere near as much. Here I'm working with the Dremel to make this hole under here larger, and I started biting off a bit too much with the Dremel. I'm going to zoom right in. Do you see how the colour, I've got all the blue powder here, and do you see the yellowy tinge to this part here? So keep an eye on the colour as you're drilling or grinding, and if it starts changing to that colour, it's an indication that it's overheating. So it still wasn't, there was no smoke sort of coming out, but yeah, the colour started to change of the drillings or the grindings. And that's all. Thanks for watching.